Hey, welcome to Ones and Zeros. My name's Ben, and today we're going to be taking a look at the next video in our STM32 Basic series, where we will be going over the SPI bus, or Serial Peripheral Interface, which is used to be able to connect the STM32 devices to other ICs or other chips to be able to send and receive data to them, to be able to control them and allow them to be interfaced with the STM32 devices. Stream looks like it's behaving, which is awesome. So what we're going to do is firstly have a bit of a look at what the SPI bus is, the different signals that are required for it to work. And we'll have a bit of a look on the oscilloscope at what those signals kind of look like so that we can actually sort of see how they work. And then we're going to have a bit of a look at how we can actually make use of the SPI peripherals inside the STM32 devices to be able to communicate with the other devices. And once we've done that, we're going to go through, as we have done in our previous videos, and we're going to take a bit of a look at getting a driver written to be able to more easily make use of the SPI peripherals in a bit of a more dynamic way. So that's kind of the plan for this video. So let's get stuck into it. So we have this particular device here, which we're going to be working with. See if we can get the camera to take a bit of a look at that one. So we've got our STM32 F411 Nucleo 64 board, as we've used in a bunch of these videos previously. And we're going to have it talking to this IC here, which is on little breakout board, which is basically a 0.5 megabyte memory module, flash memory, that we can use to be able to store bits of data and things like that. So the particular chip that we're using for that one, if we jump over to this screen here, is an Atmel device, and it's the AT45DB041D, which is a bit of a mouthful, as we can see there. So this one communicates via SPI bus, and we can see that we can get that to communicate at up to 66 megahertz. So as far as performance, it does allow us to be able to read and write to the flash memory fairly quickly, not as quick as we could do using quad SPI or things like that, but still not a bad chip if you need to be able to store, data logging, things like that. It's not huge in terms of its capacity. Like I said, 0.5 megabyte. You can't store a huge amount of data there, and there is sort of larger variants that you can get hold of, but it's going to be perfect for getting a bit of an example today so that you can sort of see how SPI works, especially because it does have a chip ID register which we can read to be able to make sure that we are getting solid communication to and from the chip. So that's what we're going to be looking at. And then if we jump over to get our camera pointed in the right direction, we're going to have a bit of a look at what some of those signals actually look like. So let's get that camera sorted out. Let's jump over to that one. So what we're looking at here is a bit of communication between the STM32 and that flash memory module. So this is on the oscilloscope. Zoom out, you'll be able to see that one there. So essentially there's 4 different signals that we use when communicating via the SPI or SPI or Serial Peripheral Interface. And we can see those there. So let's jump over to this screen and we'll draw a bit of a diagram so that we can sort of see what those are, and then we'll jump back over to the scope and have a bit of a look at what they actually look like when those signals are working. So if we have our, make sure this is actually working for me, might help. Bit of a technical difficulty. Let me just get this sorted out. That's better. All right. Apologies for that. So if we jump over to this one, if we have our STM32 device, excuse my messy writing, then connecting that up to another device using SPI, as I mentioned, we need 4 particular signals to be able to communicate with that. So let's just pop a device over here and we'll get our 4 lines connected across to those. So the first one which we are going to need is our chip select line. Now you'll sometimes see that one written as NCS, and part of the reason for that is because that chip select line is an active low signal, which means that it's typically going to be high, but the signal will actually go low when it goes to communicate with that particular device. And then the other 3 signals that we will have, didn't leave myself much space to be able to write them. Get that back there, is our clock signal, and then we have a MSOI signal or MOSI, and then an MISO signal or MISO. So those last 2, the MOSI and the MISO, basically stand for master out, slave in. So that's when the master's transmitting and the slave's receiving. So it allows us to send data. In this instance, if the STM32 is being the master device, it will allow data to be sent from the STM32 to the device. So that goes in that direction. And our MISO signal goes in the opposite direction and stands for master in, slave out. Our clock signal will also go from the master device to the slave device, as will our chip select signal. So as we can see there, 3 of those signals are going from the master, in this case the STM32, over to our device. In the case of what we're using for the example, that'll be our flash memory. So we just pop flash in there so that we know what we're talking about. And we can also go through and hook up multiple devices to our SPI bus. However, for each additional device, we do require 1 additional pin or 1 additional signal line. So we can't share our chip select signal in between multiple devices. However, we can share our clock, our MOSI, and our MISO signals in between multiple devices. So for example, if we were to have another device, let's pop one over here, then we can take our clock signal and send it to that one, and our 2 data signals, and they can go down to that one. But we would need to grab an additional chip select or NCS so that we know it's active low, and that would allow us to hook up another device. And we can hook up as many devices as we like, but we're going to have to give 1 individual chip select pin to each of those devices that we're connecting. So it's quite a good bus though in terms of performance. We can get quite a bit of data sent and received across the bus, and it's also bidirectional due to the fact that we have both a signal for transmitting data as well as a signal for receiving data. So it does use more pins than, say, if we were using the I2C bus, but because we're not doing the additional things like sending the address and all of that sort of stuff and having the acknowledgements happen over those signal lines, in some ways we can actually get slightly better performance over SPI than we can with I2C. But the limiting factor is basically the fact that it does use more GPIO, so a minimum of 4 to be able to hook up 1 device plus 1 additional GPIO for each extra device that you wish to hook up to that bus. So that's kind of how the connection side of things works. If we jump back over to our oscilloscope, we can actually see our 4 signal lines. So we can see the yellow one, which is our chip select signal, our purple one or pink one, which is our clock signal, Our blue one is our master out slave in, or MOSI signal, and our last one, the green one, is our master in slave out signal, so the data coming back from the device. So in this case, we've got 4 bytes being transmitted. So we can actually see there's a slight gap in between the clock signals there, and then we've got basically groups of 8 clock signals there, 4 groups. And we can see the start of the actual transaction happens when the chip select goes low. So we can see how it's normally high both at the start there as well as over at the end. And then that goes low. The clock will pulse as the data is sent. So we can see here that we're actually sending 9F in hex as the first byte, which is being sent over to our slave device. And then we can see the slave device sending back some data here in the form of the first byte, which is 1E, followed by 00 and 00 for the last 2 bytes. So that's kind of what those signals look like. You will notice in some cases, depending on the particular device, as we can see here, there's a little bit of noise on our MISO signal line. And that tends to be fairly normal for some devices because they've basically got their transmitter, I guess, turned off in that instance. So what we're seeing there is basically noise from the clock signal as well as the MOSI signal being picked up and sent back. However, when the device turns on its transmitter on the MISO line, we can see that that noise basically disappears at that point, and then we start to get clean data from it. So in this instance, because we're transmitting the first byte rather than receiving anything, we'd actually just be ignoring this noisy bit here, and then we'd actually be listening to the data that's coming back on the remaining 3 bytes that we've got there. So that's kind of what those signals look like. Gives you a bit of an idea of how they work. So let's jump into some code and let's see what that actually, how we actually make that work with our STM32 device. So we'll jump over to this view here, and this code is the same code that we were working with during our last STM32 basics video, so the one where we took a look at the I2C bus. I have just removed the bits in here that we had for actually communicating over I2C in preparation for getting the SPI bus stuff done. So this code will be available from our GitHub typically about 10 minutes after the end of the stream. So if you want to check it out, that's jump on there. You'll be able to have a look at it or download it and mess around with it. It is free for non-commercial use, so if you want to try it out on your own devices, have a bit of a play with it and see how it works, feel free to do that. If you do want to use it for commercial purposes, you would need to actually get in touch with us on our email address, and we can potentially discuss options there. But what we're going to do first up is basically just get the SPI set up so that we can actually get communication happening with that flash chip. And once we've sort of seen how that works, then we'll actually look at going through and getting a driver written so that we can be able to access SPI devices a bit more dynamically. So first things first is we're going to need to set up our GPIOs. So we're going to need a GPIO init type def for that one, which we're just going to call GPIO init and fill that one with zeros. We're going to do we might do our clock signal first. So that one, can't remember off the top of my head. Make sure that I have the right pinouts for this one. That may actually help, otherwise we're not going to get any communication happening with that one whatsoever. So that one, I believe we are looking at pin A5 for that. Let me just double check that, which is correct. Okay, so Our pin for that one is going to be pin number 5. We're going to want to put that into output push-pull mode. We're not going to use any pull-up or pull-down on that one, so just put in GPIO, no pull for that one. Our speed, we're going to put the speed for that one all of the way up. Just get that out of the road. And we need to set up our alternate for that one as well, so it knows which peripheral we're actually connecting that to. In this case, that is going to be alternate function 5, SPI 1. And we'll initialize that one. So that's on port A. And we'll pass it a pointer to our GPIO init structure there. Now, make things nice and easy, let's copy and paste this a few times. Tidy it up a bit. And fix up our indents. There we go. So I'll do our master out slave in signal next, which will be on pin 7. That's going to use the same settings, so output push pull, no pull up or pull down resistor, high speed, and that one is on the same alternate function. Our MISO signal is on pin 6, and then our clock signal, not our clock signal, our chip select signal is on pin 4. Now, with the chip select signal, we are going to use the pull-up resistor because, as we mentioned before, the signal is normally high and it goes low whenever we actually want to communicate with the chip. So just going to use the pull-up resistor to make sure that that signal is pulled high as soon as we initialize the GPIO. And they're all on GPIO A, which means that's all correct. Should be good to go. Now, next thing we're going to need to do is enable the clock for our SPI1 peripheral. Let me make sure I do that one correctly. So that'd be SPI1 clock enable. And just reset the clock on that one as well, like so. Now we'll go about actually initializing our SPI peripheral. So for that guy, we're going to need hiding from me. There we go. Should be able to remember that one off the top of my head, but I don't. Not enough coffee this evening. So let's just call that one SPI handle. So we use the handle type def to be able to communicate with the SPI peripheral using the HAL. As well as using that to fill out our initialization options for how we actually want that to work. So first things first is we need to tell it which peripheral we're using. In this case, it will be SPI1. And then we fill out the initialization details as we want them for this one. So in this case, we are going to want might help if I have the bits I need ready to go. Okay, so first things we're going to want is to tell it which mode we want it operating in. So in this case, we want the STM32 device to be the master device. So we'll let it know that we want that in master mode. We want to tell it which direction we're going to be communicating in. So that'll be that one there. And in this case, we're going to go with 2 lines like so. So you can set up SPI just to do one-way communication as well. And you can either set it up to just do transmit or just to receive and set it up as needed there. But in this case, we want to be able to both send and receive data to be able to test it and make sure it's working properly. So that's what we're going to be using there. And we need to tell it the size of the data that we're going to be using. So in this case, we're going to go with 8-bit. You can also set it up with 16-bit as well. But the particular flash memory device that we're using here just does 8-bit communication, so we're going to stick with that one. We need to tell it what the clock polarity is, and that'll be dependent on what device you're actually communicating with. So that can be either high or low polarity. In this case, still can't type properly, excuse me. We want that one set to low. We want to set our clock phase, and we can either set that to 1 or 2 edges. In this case, we're going to go with 1 edge. So that will be SPI phase 1 edge, like so. We need to tell it whether or not it's going to be controlling the chip select or if we are going to be controlling it. Now, in this instance, we might get it to do it in hardware using the actual SPI peripheral. You can also do it manually as well. In a situation where you have multiple devices hooked up to the SPI bus and multiple chip select lines, then it's a good idea to be able to be doing it manually in that instance. However, because we've only got the one device hooked up to it at the moment, we're going to go with hardware for that one. So that'll be NSS hard, and that will be an output. We'd go with an input in the instance where the STM32 was being set up in slave mode, for example. We also need to let it know what speed it's going to be operating at. Now, this is based on the particular clock that is being provided to the peripheral. So you can select multiple different clock sources and go through and set those up as needed. We're going to stick with the clock as it is at the moment, just in its default operating mode. If we jump into this file here, we'll be able to get a bit of a look at where it's getting its clock from by default. I believe by default it's just going to be pulling it from its particular peripheral bus. So being a little bit slow to open up. Alright, so if we go into our clock configuration, it's not actually going to show us for the SPI devices on this particular device. It does for some of the others. So yes, we'll do that. Let's just find jump into our data sheets. Wrong device. We want STM32 and we want the F411 Nucleo. We'll open up. Actually, let's go with just the normal data sheet for this one. And let's have a look. So as I mentioned, by default, we should just be pulling the clock from our particular peripheral bus, and we can see SPI 1 is connected to peripheral bus 2, which is operating at 100 megahertz. So we can assume, based on that, unless we want to go and mess with the clocks, that we've got 100 megahertz there. We know that our particular device can operate at up to 66 megahertz, but just to keep things simple, we will go through and set our baud rate prescaler. We might just go with 16 for the moment. So basically it's going to take that 100 megahertz clock, divide it down by 16, and that's going to be the particular clock that we get out of that. So if we take a look at that, we're getting about 6 megahertz worth of clock speed out of that, which is still not too bad. We could definitely just adjust that. So even if we adjusted the baud rate prescaler to 2, then we should effectively be getting a 50 megahertz clock, which is still going to be fine as far as the particular speed ratings for the device we're using. However, the fact that we've just got it wired up using the patch wires that we're using for that one means that it can be subject to some interference. So these wires can pick up some interference, which may affect its ability to be able to communicate at a higher speed. So it's worth factoring that in too. It's always better off starting at a slightly lower speed and then working up once you know that the communication is actually working correctly, and then seeing sort of where things may start to break down. So that's our baud rate prescaler. We also need to let it know whether we're transmitting most significant bit or least significant bit first. So that will be our first bit setting. And in this case, we're going to be going with most significant bit first. So that will be SPI first bit MSB. We also need to let it know the TI mode. In this case, I don't believe we're using the TI mode. I think that one's going to be disabled, which is correct. We want to let it know whether or not we're using CRC. In this case, we're not going to be. So that one we will set to disabled. So SPI CRC calculation disable. And then lastly, we're just going to set the CRC polynomial to 0. We're not actually going to be using that anyway, so that's not going to be an issue there. So let's get that one initialized. So it's just a matter of calling HAL SPI init, passing it a copy of or a pointer to the handle, like so. I'm going to make sure that that actually initializes correctly. So if it fails to initialize properly, so if we don't get HAL OK back, then we will send out a message via our UART over ST-Link just to let us know. And we'll turn on our user LED so that we know that there's an issue, and we'll just jump into an infinite loop at that point because we don't want to continue if it's not working correctly. Now, just make sure I've got up the bits that we're going to need. At this point, we should be good to go as far as getting that up and running. So if we get to this point, we'll pop a message out via UART just to say that that has successfully initialized. Like so. So next thing that we're going to do is actually go through and just check that we are getting valid communication. So we're going to make a couple of uint8t arrays. So one for what's getting transmitted and one for what we're actually receiving back. So let's just call this data tx, and the byte that we're going to be sending is just to request to read the chip identification register. So we'll also go with our receive data there and just make sure that I've actually got that register address correct. Let's jump into here. Where are we? There we go, manufacturer and device ID read. So we need to be sending it 9F, which I believe we've got there. That's correct. Excellent. So now we've got a place to store the data we're sending and the data we're receiving. We can go through and actually get that working. So in this case, we're just going to go HAL SPI transmit receive, because we do want to be transmitting and receiving at the same time. We're going to ignore the first byte that we get back from the flash device because it's not going to send anything to us for that first byte, because it's waiting to hear which register we want to access, in this case 9F, or the manufacturer and ID register. However, it will fill the 3 remaining bytes with data that we can actually check and make sure that we're receiving the correct data. But because we are using the transmit receive method for all 4 bytes, we do need to supply it with enough space to be able to store those 4 bytes for our receive buffer, as well as being able to transmit 4 bytes in our transmit buffer. So that's why we're using 4 for each of those, and that's why we're setting the remaining 3 in the transmit buffer to zeros, and then just going to ignore the first byte in our receive buffer. So first things first, we need to hand this a pointer to the handle, and then we'll give it a pointer to our transmit data and a pointer to our receive data. Let it know how many bytes we're going to be sending and receiving, so 4 in this case. And then we need to supply it with a timeout value as well, which in this case we're just going to set it to 1000. Now we'll also check to make sure that this one works correctly as well. So if that fails, then we'll send out an error message as well. Now, although this is called transmit receive, I generally shorten that to transceive for most of the methods and things like that, which is why I'm using that there, just because that does sum up both transmitting and receiving at the same time. Now, assuming that that has actually worked correctly, let's get a string that we can write some stuff into, and we're just going to use sprintf to format some stuff in there. So just going to get it to format 3 bytes as 2-digit hexadecimal values so that we can see those 3 bytes that we're getting back from our flash device. Like so, and then we'll send that out via serial as well. So just send our string out to that one. So as we can see, gone through and we've set up our GPIOs for our 4 pins that we're using. We've enabled the clock for the SPI peripheral, gone through and initialized that one with the settings that we need to be able to communicate with the device, and then done a bit of test communication just to be able to see that we are actually getting the correct data back from our device. So let's build that and make sure that builds correctly. Zero errors, zero warnings, always a good thing to see. So we will grab our serial monitor and get that one connected to our STM32, and let's pop that software over onto that one. All right, and we can see that we are not getting the data we expected, so we're actually getting all zeros back from that one, which is a little bit strange. If we reset that one, we're still running into the same issues. So got ourselves a little bit of a bug to figure out there. Just double check our wiring to make sure that that is all connected correctly. Still not getting what we want there. So what we might do, just to make sure that we're actually transmitting correctly, let's get the scope connected up to that one. Thankfully, it's just about ready to go, so connect that one up like so. Now let's jump over to this camera. So we can see, thankfully there is a pass through for the pins on this board. So basically just hook the scope up to those pins there. And then we've got a couple of ground connections just so that the scope can actually get a ground reference as well. Let's jump up to the scope screen so that we can see what's coming up there. I'm going to hold down the reset button just because the chip select signal is the one that we're triggering off, and that will go low when we reset the device. So just put that in single shot and release that one, and we are not getting anything at all. We're actually getting a pulsating signal there. Maybe if it may be because our clock is set so low. Let us just modify the clock rate on that one, and let's see what that gives us. It's a bit of an interesting problem to be having. Might just change our trigger to channel 2, and we're going to set that to trigger on rising edge. I'm curious what this clock signal is that we're getting, which is a little bit strange. It's quite a slow clock signal that we're getting there as well. Let's have a look at what we've got there. So getting a 2 Hertz signal out of that, as we can see from actually no, that'd be 4 Hertz because we're looking at half a clock period. It'll be 1 Hertz. Sorry, maths isn't working in my head properly, which is a little bit strange. So we are possibly missing something. Let's have a look at what we've got. Now we're not getting any error message to say that it has failed. So if we jump over to here, we can actually see that as far as the HAL is concerned, it has actually initialized successfully, and we're not getting any issue transmitting and receiving, which is a little bit strange considering what we are seeing on the scope screen. Let's just double check. What errors do we have? Ah, okay. Added this bit just to make sure the peripheral's being enabled, which the HAL should be doing anyway, but let's just build that, make sure that that works properly. So we've got our instance, mode direction, data size, clock polarity, clock phase, chip select, baud rate, prescaler, first bit, TI mode, CRC calculation are all correct. Have modified the baud rate prescaler to 4 just to see if that had any impact on the speed of the signal that we were seeing on the scope, but it didn't. And so we definitely want mode master, 2 lines, data size is 8 bits, clock polarity is low, and phase is 1 edge, which is correct. I'm using hardware chip select. First bit is MSB, TI mode is disabled, and CRC is disabled, which is all correct. We are going through and initializing that one. Shouldn't actually need to enable it because again that should be done by the HAL. So there is definitely something a little strange. Let's pop that on the device. Still getting the same result. And still not getting any error from that one at all. I'm just going to have another look at that clock signal. It's definitely a 1 Hz signal that we're getting, which doesn't match with what we should be getting. It should be a decent bit quicker than that. Do we have our pin set up correctly? Pin 5, pin 7, pin 6, pin 4, that's all correct. We're pulling up our chip select pin, which we're also not seeing as being pulled up on our scope, which is another strange thing. Makes me think the peripheral's not working correctly, which means we've probably not set something up correctly. The chip's not locking up either. If we jump over to this one, we can see that the LED is flashing, so we do actually have a heartbeat happening from our device. So that is working correctly. Alright. This one has me scratching my head just a little bit. Jump back over to that one. That stuff is all correct. Let's make sure that things are actually getting initialized correctly. Let's pop a breakpoint in there. We'll jump into debug mode. I'll switch over to our debug view. And let's run it to that breakpoint. So at this point, we should have it actually initialized. Let's go through, find SPI1. And there's actually going through and setting up the device correctly. Now, not seeing anything on the scope as of yet. Let's get rid of our cursors. We'll center our trigger point up a bit. Okay, so after the point that we're looking at on the debugger is when we actually start to see that clock signal doing what it's doing. Always like a bit of a challenging problem. Let us pop a breakpoint in here. And we're going to terminate that one. We'll relaunch it into debug mode. I'll jump to that first breakpoint. As we can see, nothing on the scope as of yet. And let's pull up our SPI peripheral here. You can see all of the values are reset in its registers. They're all zeros at this point. So clock's enabled. Going through and filling out the details in our init structure. And we can see values in our control registers change when we go to do the initialization. We are getting a successful thing back from that one. And we can see on the scope, even at this point, our clock chip select pin is sitting low, which it shouldn't be. Now, you guys are probably screaming at the screen because some clown hasn't actually set the pins up in the correct mode. So these should all be alternate function push-pull. My apologies for that. Explains why we were getting some weird behavior. So we'll terminate that one. Pop the scope out of roll mode. Let's build that one. Gives you a bit of an example of sort of the approaches to actually getting something like that solved though, and how you can track down where the error is. It does tend to be a little bit harder to spot more obvious things on stream, but got there in the end, and I'm pretty sure that's going to solve our problem for us. So let us run that. We're going to change our trigger back to channel 1 on the scope and on falling edge, so that it's triggering based on the chip select line. And let's see what we get from that. Alright, looks like we're actually getting correct stuff happening there. Let's just trigger that again. That might help if we can actually get to the correct spot, and that is looking a lot healthier. Let's go to about there. Much better. So now that we've got that sitting on the scope screen where we want it, let's trigger it one more time. Just move the position of that one again. Okay. Now, looks like the scope's actually picking up some noise there. So we should actually be seeing 9F, but we're seeing 9E. It may also be that we don't have our decode set up 100% correctly. I don't think it's going to let us adjust our number of clock edges and our clock phase there, but let's see what we are getting back from our device. So we can see, clear that, let's reset it again, and we can see we're getting actual data coming from the device now, which is 1F24 and 00 in hex. If we jump over to our data sheet, we can see that what we should be getting is 1F2400, which correlates with what we're getting here. So we are successfully getting stuff transmitted and received to that one. So apologies for the distraction of trying to find that very silly bug, but again, gives you a bit of an idea of some of the approaches you can use to be able to solve those sort of bugs, and also shows why it can be really useful if you've got a 4-channel scope that can do communications decode, where you can actually use that to be able to track down specific errors. It may have been a bit harder to be able to find that error if we couldn't actually see what signals were coming up, and the fact that we were getting signals that were quite weird for what we were actually looking for. Now, the one thing that does make me a little bit curious is that 1 Hz signal. But if we have a look at the board at the moment, we can see that we no longer have a flashing LED, and that LED is set up to flash at 1 Hz. So if we jump into our settings here, we can actually see our clock pin that we're using is actually also wired to our user LED, which would explain why we were still seeing a signal there, even though the pins weren't set up correctly. So that would explain that one, and a good reason why you want to check which pins you're wiring various things up to at any point in time. So I'm just going to take a quick bio break, and then we're actually going to have a look at getting the driver sorted out for this one. Make sure that that one works correctly and go from there. So I shall be back in a couple of minutes. And we are back. Alright, so first thing we're going to do is just comment out the bits that we popped in here just for the testing. So I'm going to replace this with what we're doing with the actual driver itself. So just get those out of the road. I'll leave those in there so that if you want to jump on GitHub and check that code out, you'll be able to do that. And let's get us a driver written. So let's close some of these files we don't need at the moment. Now, much like we've done with our timers and our I2C peripheral, we are going to firstly set up a peripheral manager for the SPI peripherals. So let's get a couple of files created for those guys. So SPI manager HPP, no template for that one. And our source file. And while we're doing that, let's also get the files prepared for our actual driver as well. So the reason why we do the manager is so that we can make sure that we don't have two drivers trying to access the same peripheral at the same time, which could potentially cause us a few issues, so we don't want to be doing that. Let's grab hold of our header from one of our other files and we'll copy that guy across to here. Modify our header to suit. And date today is 13th of December. Alright, so that's that one. We want our prevent recursive inclusion, so pop those guys in there. Like so. Let's grab all of that and copy it across to our source file. And get rid of our recursive inclusion stuff. And that should be CPP for that one. Just save that file, paste that in here as well. And we are missing an R from those guys, so let's just fix that up. That's a bit better. And fix these guys up. And we will paste that in here as well. Alright, and we also need to make sure that our source files are including our headers, so we'll fix that up like so. That one should be manager. Make sure we get that correct. And our SPI header file also needs to include our manager header file as well. So that's got our 4 files ready to have some code popped into them. And we're going to go through it and do a little bit of copy and paste just to make things a little less boring. So first things first is some enums, which we'll pop in here. So first of these just basically allows us to select which of the peripherals in this device we're actually talking about. So when we go to register one as being in use or deregister one or things like that, we can actually let it know which peripheral we're actually talking about. And we've also got a constant here which allows us to keep track of how many peripherals we've got in this particular device. Excuse me, losing my voice. Might help if we jump over to the correct screen. We're doing great this evening. So, got our files all created there. We've got our peripheral enum, which allows us to select which peripherals we're talking about, as well as our peripheral count, which allows us to tell how many peripherals we've actually got, as I mentioned. And then we've got a few states here, which allows the manager to be able to keep track of what the state is of each of the peripherals. So whether it's not being used, whether it's being used in SPI mode, or whether it is being used in I2S mode if we're using it for audio. So we will look at I2S in a future video. Now we're also going to set up a structure which will contain the information for each of the devices or each of the peripherals. So keeping track of what peripheral it is, what state it's currently in, as well as storing a SPI type def so that we can be able to retrieve that for a particular driver to set up that peripheral, what the IRQ is for that particular peripheral, as well as what mode it's being used in, or actually whether it actually supports I2S, which for the 5 peripherals on our STM32 F411, I believe they all support I2S mode. And then let's get our actual manager itself. So we're going to have this one set up as a singleton class, so similar to what you may have seen in some of our previous videos. Let's fix up our indents here. So basically setting it up as a singleton class because we only want one manager class to be able to exist. And data we're storing in here is basically just an array of our QAD SPI data structures there, just to be able to keep track of the various peripherals. We're deleting our copy constructor and our assignment operator to prevent more than one copy of the class from existing. We've got our singleton method, which allows us to retrieve a reference to the instance of the class. And the way that works is the very first time that this get method gets called, it will call our constructor, which will be defining the code for that in our source file. So we've got some of our static methods which allow us to be able to actually access the class, and we'll kind of see how they work when we go through to start setting up our driver. And then we've got the implementation methods that match up with a bunch of our static methods. So the static methods are the ones that we access from outside of the class, due to it being a singleton class, and then as we can see they then call their respective implementation method. So we will be doing a video on singleton classes a bit more in depth in a future video with our Unearthing C++ videos. That one will be coming up soon, possibly in the next week or two. Now let's go through and actually get some of our code copied into our source file. So the first thing we want is our constructor, which will basically go through and fill out some of the details in our data structures. So these guys here. So basically going through setting all of the peripherals to being unused, and they do all support I2S, so we're setting that flag to true. On some STM32 devices, I believe you do have situations where your SPI peripherals, you'll have some that do support I2S and some that don't. So we're including that in here just to make the code a little bit more portable for when we actually go to port that over to other devices in the QuartzArk codebase. We're going through and setting the peripheral IDs for each of those. So that's just the enum that we set up in our header file. So that's this guy up here. And then setting our instances for those, which the driver will be using when it goes to actually initialize a peripheral, and then our IRQs. So that's those guys there. Next, we've got our management methods, which will pop in there, fix up our indents, like so. So this one is used when we go to actually register a device from our driver. So the driver can actually firstly check whether or not the SPI peripheral is currently being used or not. And if it's not, then it'll go through and register it as being used. And the driver will also let it know what state it's being used in as well. So it's basically passing to it which peripheral we're talking about, which is the eSPI, and then our eState, which tells it whether we're using it in SPI or I2S mode. So see, basically just getting that set up there, and then our deregister method, which the driver will use once it's finished using the SPI peripheral, just so that the manager knows that that peripheral is no longer in use, and that way if another driver comes along and wants to use it, it'll be able to do that. Now we also got some clock methods, which allows the manager to be able to enable or disable the clocks for the various peripherals. So this is another thing that will be accessed from the driver. So the driver can go through and enable the clock or disable the clock respectively. And similar to what we saw before when we were setting it up, it just goes through and enables the clock, does a force and release reset on those ones, just so that that clock's enabled and ready to go for whichever peripheral we're in the process of setting up. And then when we go to disable it, it's basically just calling the clock disable method to be able to disable that clock for the particular peripheral. Lastly, we've got a couple of methods which allow us to keep track of how many SPI peripherals are currently in use, or how many aren't in use. So get SPIs active and get SPIs inactive, so that when we go to start implementing some stuff for our operating system, we can actually get the operating system to be able to keep track of how many peripherals we're actually using or not using at a particular point in time. So that's why we're including those guys there. So that's basically our manager. Now let's go through and actually get the driver itself done. Again, just going to be doing a bit of copying and pasting just to keep things flowing a little bit. Now, in order to get the compiler to help us a little bit more as far as getting things set up, we've got a whole bunch of enums which we're setting up here. So basically, when we go to initialize a particular device with a specific set of settings, we're basically going to be using the enums to provide those settings rather than using the HAL defines directly, so that the compiler can actually check that we're providing the correct details for specific bits of information for each of the details that we need to provide to the driver. So we can see got all of those guys set up. So similar to what we're doing in here, but rather than providing the HAL defines, we're actually using the enums instead. Again, just for keeping things a little bit safer. That way the compiler can double check what we're doing a little bit better as well. So we've also got an initialization structure. So basically this structure will get filled out with the required details for how we want the peripheral to be set up. So providing it similar sort of details to what we'd be providing the HAL here. So we can see all of the details for how the peripheral is actually going to be set up, as well as details for the GPIOs and things like that. And then we've got the actual driver class itself, which, let's grab that one and we will copy that over to there. Fix up our indents. Grab all of these ones as well, move those over. Move that private section back over there, that's a bit better. And that'll be that one, fix those indents there, wonderful. Alright, so we can see our QAD SPI driver class that we've got here. So we've got our deinit mode, which is used to allow us to either do a full deinitialization if we've got the driver completely up and running and the peripherals initialized correctly. We've also got deinit partial, which is basically used in a situation where we've gone to initialize the peripheral, something hasn't worked, and we need to deinitialize part of the stuff that we've got set up there. So we'll sort of see a bit more about how that works when we get onto the initialization methods. We've got the timeout value that we're using. In this case, we've just set it to 65535 or FFFF in hex. We're keeping track of whether or not the driver is actually initialized and whether or not it is actually active. Those enums are defined in our setup.hpp file up here. So now not initialized or initialized, now inactive or active. Just allows us to keep track of that one a little bit easier. We've got the keeping track of which peripheral we're using, what the IRQ priority is, as well as the particular settings that we're using for that one, and the details for our GPIOs, as well as the particular IRQ that's used for that one and our handle type def, so that we can use that to access the HAL methods. We've got our default constructor being deleted here simply because we need to be supplying the class with an init struct with the required details when we go to create the class. So delete the default constructor and then set up a constructor where it's actually getting past the initialization structure, and then going through and storing a bunch of the details that we need from the init structure, as well as setting up a couple of other details there. Then we've got our destructor, which is this guy here, which when we go to destroy the class, it's firstly going to check and see if the driver is active. If it is, then it's going to deactivate it. And if it's initialized, then it's going to go through and deinitialize it. So when we go to destroy the class, it's going to mean that the peripheral and the GPIOs are back in the state they were in prior to us actually setting them up in the first place. So making sure things all work the way they should. We've got our initialization methods to go through and actually initialize and deinitialize our driver class. We've got the details so that we can retrieve what state our driver's in, whether it's initialized or not, as well as to be able to retrieve the handle type def if we need to do that as well. We've got some control methods to allow us to start and stop the driver, as well as to check whether the driver is active or not, as well as some communication methods so that we can transmit, receive, or do transmit and receive at the same time. And then we've also got some private initialization methods, and we'll see in a moment why we've got some private ones and some public ones as well. There's a bit of a reason why we do that. So let's save that and let's get some code popped in our driver's source file. Starting with our public initialization and deinitialization methods. copy those guys across. So as we can see here for our initialization method, just going through and firstly checking to see whether that peripheral is available. If it's not, then it'll return a error saying that it's busy. Then if it's not busy, we'll go through and register that with the manager so that the manager knows that we're now going to be using that peripheral. And then we'll go through and we'll call our perif init method there. So that way we're actually doing the particular checks that we need to do with the manager prior to calling this private initialization method. And then if that fails, so if we get a result back that is anything other than success, then we'll go through and deregister that from the manager to say that we're no longer using it. And our perif init method will actually go through and deinitialize things if we have a failed initialization. So say it goes through and it gets the GPIO set up and then goes to initialize the peripheral and something fails, then it will actually go through and sort everything out so that, again, everything is in the same state that it was in prior to actually getting the driver initialized in the first place. Our deinitialization method will firstly check to make sure that the driver is actually initialized. If it's not, it's just going to return. Then it will go through and deinitialize everything and then let the manager know that it is no longer being used, so that that can then be used by another driver, or if we go to reinitialize this driver again, things like that. So we can see, as I mentioned, with the manager being a singleton class, the particular way that we go about accessing that is by using the class name and the 2 colons, and then we can actually access the particular static methods that we've created in there. So if we scroll down in our manager class to, say, our deregister method, these static methods are the ones that we're actually accessing. And with a singleton class, the way we access those is by using the class name followed by the 2 colons. And then we've just got our method to be able to retrieve whether or not driver is initialized, as well as retrieving our handle type def if we need to do that as well. So let's move on to our control methods. Fix up our indents for these guys. And these guys are just going to go through and actually enable or disable the peripheral. Now, depending on which mode you're using, so in master mode, for example, you don't necessarily need to go through and actually enable or disable a peripheral. That stuff will be done by the HAL. However, if we were putting it in slave mode, for example, which this driver also allows us to do, then we need to enable that prior to it being able to receive data, for example, and depending on how we actually go about setting those up. So that's why that one's there. Losing my voice a little bit at the moment. We've got our communications methods. Fix up our indents. Now this driver also allows us to put the chip select pin into software controlled mode, and we can have the driver take care of handling the chip select pin if we would like to. In that case, essentially when we go to initialize it, we're going to do it that way, so you can kind of see how that works when we go to test it. But it basically means that we have the option of either getting the peripheral to do it in hardware, we can get the driver to do it in software if we're only connecting one device up to the SPI bus, or if we're hooking multiple devices up, we would actually tell the driver that we don't want it taking care of it, and we would actually do that manually outside of the driver whenever we want to communicate with a particular device. At some point, we might go through and actually set the driver up so that it can deal with multiple devices, but for the moment, we're keeping it a little bit simpler and just doing it that way. Now the last couple of methods are the largest ones, which are where we actually get the peripheral initialized and deinitialized. So again, we'll just go through and fix up our indents. Fix that one up as well. Fix that one there and fix these guys up. So having a look at our initialization method, just going through and getting our GPIO set up, and depending on how we get how we're looking at setting up the SPI device will depend on how it goes through and sets up the GPIOs. So our clock pin's pretty simple. We're just going to set that up as needed there. Our Mozzie and MISO pins will depend on whether we're operating in master or slave mode, or whether we're using 2 lines or 1 line, or using bidirectional, for example. So this is going to go through and figure out whether or not the Mozzie pin is actually being used, and then we'll set that up accordingly if needed. Same with our MISO pin. And then as far as our chip select pin, if we're using hardware chip select, it'll go through and set it up for that. If we're using software chip select and getting the driver to take care of it, then we will set that up there. And then enabling our clock, so just asking our peripheral manager to take care of that for us, and then going through and initializing our peripheral. Now, if we get to this point and this fails, then it will ask our perif deinit method to do a partial deinitialization, which will then go through and disable the clock and deinitialize the GPIO so that everything is back in the same state it was prior to starting the initialization. We're also setting up our IRQ priority and enabling the IRQ for that device so that if we do want to go through and actually use that, then we can. Again, that's something we're going to have a look at in a future video. We'll also potentially have a look at using DMA and things like that in a future video as well, but just basically setting the driver up so that it's good to go for things that we might want to add or change, stuff like that in the future. And we can see that it's actually retrieving the particular IRQ enum from our peripheral manager as well, so that it knows which IRQ is being used by this peripheral. Now, as far as our deinitialization, so if we're doing a full deinitialization, then it will go through and do this stuff as well. So disabling the IRQ, making sure the device is no longer active, and then deinitializing the peripheral. If we're doing a full deinitialization or a partial one, it will go through and disable the clock and deinitialize our GPIOs as needed there. So, and again, checking to make sure that it does actually need to deinitialize these particular ones. Simply because we could be using those GPIOs for something completely different. We don't want to be deinitializing those if they're not being used specifically by this driver. So basically just going through and checking that stuff there. And then as we did in the initialization, just setting our states to not initialized and inactive there. Whereas we can see in our initialization method, we go through and actually tell it it's initialized, but not currently active. So that's a bit of an explanation of those particular methods. There will be further commenting coming for this code as well, but that just gives you a bit of an idea of what we're actually doing with that. So back in our main file, we're going to create a pointer to a SPI driver class there so that we can make use of that, which we'll just call SPI test. And we better include our driver header file in here as well so that we can actually access that. And actually we might maybe change the name of that, so we know we're using that for flash memory. So let's just call that SPI flash. All right, so let's get this guy initialized. Again, I'm just going to do a bit of copy and paste to make this a little bit simpler. That might help if I don't select stuff I don't want to copy over. And let's just pop a comment in here. Like so. So similar to what we do when we're setting it up with the HAL directly up here, basically going to create an init struct. We'll fill that out with the particular details that we want. We can see that we're telling it that we want to use software chip select here. In that case, it will go through and check if we're actually providing it with a GPIO here. So if we wanted to do it completely manually, we can set that to null, in which case it will let us handle the chip select. But by setting it to software and popping a GPIO in there, the driver's then basically being told that it's going to be handling the chip select in software itself, and it will take care of that for us as needed there. Going through and getting that one created, handing it a copy of the initialization structure, then going through and getting that initialized. And again, if that fails, similar to what we did before, it's just going to pop out a message to let us know, turn on our user LED and jump into an infinite loop. As mentioned, we don't always need to use the start and stop methods. It's more for if we're using it in slave mode. We can if we'd like to. It's not really going to make any difference in this instance. And then, same as we did before, we're going to go through and read our ID register just to make sure that we are getting communication working correctly with our device. So that's basically what we're doing there, similar to what we're doing before. And then just printing out the details that we read back so that we can check on those. So let's build that, see if we get any errors. Looks like it's going to compile nicely for us. 0 errors, 0 warnings, always good to see. Let's pop that over onto our device, pull up our serial monitor. Jump over to this view so we can see our device as well. And we can see that it has successfully read that for us. And we do have the same 1F2400 as we had previously. If we just reset that again, and see we get the same details again. So we are getting successful communication with that one. And just so that we can see that it is showing up correctly on the scope as well, let's do have a bit slower communication happening this time. So just zoom the scope out a little bit, and there we go. So we can see chip select's going low correctly, our clock signal's working correctly for all 4 of the bytes there. We can see the 9F in hex being sent to let it know that we want to read from the ID register. And then we can see the data that's being sent back. So again, just noisy stuff for the first byte while it's actually listening and not actively transmitting anything. And then we're seeing the 1F2400 that we're getting there as well. So let's just zoom that in a little bit so you can see that a little bit clearer. And we can see those details there for the 4 lines as mentioned. So that one is working 100% correctly, which is awesome. So that is basically how we go about setting up our SPI driver. And as mentioned, that code will be available from GitHub typically within about 10 minutes of the end of the stream. I will pop a link to that code in the description on both Twitch and YouTube as well. So hope you guys enjoyed that. If you did, would love it if you followed us on Twitch or gave us a subscribe and like on YouTube. That would be awesome. We've just hit 120 subscribers, which is pretty awesome in a fairly short period of time for this sort of content. So really happy to see that, and love it if you leave a comment and let us know what you thought of the video, things like that as well. Always good to get a bit of feedback. Again, feel free to jump onto GitHub, give the code a try, see how we've done the particular things. If you do have any questions, feel free to leave a comment on YouTube, or there is also our Gmail address and our subreddit there that you can jump onto to be able to ask questions or things like that if you need to as well. So that's it for this video, and hope you enjoyed it, and thanks very much for watching.